So how's everything coming along so far? Especially the projects. I've only talked to one person about their project, but I hear emails asking if they can be 3-person group or and so on, right? As recently as yesterday. That to me means that you haven't even figured out who is going to be a project partner. Like I told people, I don't particularly mind 3 people, but there are 12 people left over, not counting Jerry. So if you have 3, then there has to be another group which is 3. Otherwise, we have a problem, right? I don't want single-person projects unless there's a real reason why you should be a single person, because the amount of work that you have to do goes up if you're a single person, because you have to do everything. And 3-person projects is, I think, a little bit too big, because then you have to do something substantial to show why you need 3-person. And besides, we have the logistical issue of having 3-person group, right? So those are all fine, but those are issues that happen before you form a group. So once you form a group, I would still like to talk to you. I'm fairly open on what you want to do. I don't particularly care what you do, because it's a more of exploration than trying to figure out what you're trying to do is research-wise interesting or whatever, right? But there's still 2 caveats. One is, I would like to get a sense of what you're doing is sort of possible, right? So for example, in the algorithm sense, if you say you wanted to show P equals NP, P not equals NP, right? I applaud your courage, but I also have to say you are kind of on the wrong track. There's no way you're going to show that in 32 days. Your presentation is in 32 days, so there's no way you're going to be able to do something of that magnitude, right? So I would like to know that you understand. You may not understand what the difficulty of what you're trying to achieve, but if it's so hard that there's no possibility that you can even make a little dent, then I would have to talk to you to make sure that you're on the right track. And other stuff is, it has to be related to operating systems in some sense, though sort of nebulously defined. So that's one of the reasons I would like to talk to you to figure out what is the issue, right? So if you want to find out how your program for data mining can be made faster, that is not necessarily OS oriented unless you kind of have some sense of how that affects, why you think that, how is that related to systems? I mean, do you have some reasoning to believe that this is systems related and not your code, right? If you find out that the algorithm that you use for your program is slow, changing the algorithm to a different algorithm would fix it and make it go faster, and you have nothing to do with the operating system, that's not an acceptable project, right? And it has to be something measurable and all those things. So there are some parameters which has to be there to make it a ghost project. And unfortunately, if you wait till the last moment and you make a presentation, I'm at a point to judge you and give you comments, right? So I can give you comments and say this is how you can change it, but by the time I have to give you poor grades, and we don't want that, right? So does that make sense? How many of you started the project? Okay, how many of you have are all set to start the project this weekend? Okay, so that's not a good sign, right? And this is not a undergrad class, so I can't set milestones for you to say, on Monday you should turn in something to show that you're working on something. I assume that you're working, but just remember in 31 days you have a presentation, and in presentation you have to come here and give a talk. So if you choose to say we haven't started, then that's a prerogative. Right? Sorry to sound me. Does that make sense? Right? How many of you are lost on what to do about the project? Haven't thought about what you want to do? How many of you formed a group? So you guys haven't formed a group? Okay. It seems like since you guys don't have a project partner and you're the only ones left, right? So that problem solved. So you guys are a group now, right? I mean, you have to be a group, or we don't have any other person for you to form a group with, so you're kind of stuck with each other. So do you know what you wanted to do for the rest of the people? Just give a sense of what you want to do, Suggs.
I guess something with wireless networks.
Mm-hmm. So that's one of the things I was talking to you about. Like if you want to do something with wireless networks, there's a systems component, there's the networking component, there's somewhere where there's overlap, right? If it's a purely networking stuff where nothing of the systems is involved, some of the projects that you had in mind, then I would have to steer it to a different direction, right? But if there's overlap, this is an operating system course. At the end of the day, I'm going to ask you for example, how would continuations have helped your project, right? So if you said it wouldn't have because it's completely unrelated to what I was doing, then you have a problem, right? So.
We were going to meet to talk about it Friday, so tomorrow, so we don't really have anything.
Do you guys have some inkling on what you want to do?
I don't know. Maybe my partners do. But
Okay. So what do you?
I have no idea.
Okay. Okay. I guess not, right? Do you have any? Did you think about any idea about yourself, like what you want to do? Think about okay. Think about something that bothers you from anything, right? I mean, operating system. I'm guessing most of you have used operating system, right? One way or the other. So, whatever bugs you is a good place to start, right? Yeah. Okay.
Also me.
Okay. So we'll have a problem with the 3-person group. So if they're 3-person group, is there another 3-person group? Okay, so then we don't have a problem. But just remember that these U3 and U3 will have to do 1.5 times the rest of the project groups, right? Actually, you could go more, but I'm just going to hold you with 1.5 because you have more people to think about and stuff. So if your project is the same scope as the rest of the project, that's not good, right? So how about you? You haven't thought about stuff. Is there some idea of where you want to go?
Yeah, I have some rough ideas.
On what topic? Okay. You part of these, okay. And you're still thinking, but do you have any ideas?
Thinking about the measuring projects. Haven't decided.
Okay.
something with file systems. I haven't decided exactly what the file systems, but in that direction.
Okay.
Yeah, we are partners. We need to talk tomorrow morning. I want to do something in cache coherence, but we haven't discussed yet. So
Yeah.
tomorrow we will go through.
Yeah, cache coherence is another thing I think is it may be too hard for you to. I mean, if you've done something with it, that's good. Cache coherence figuring out what's going on with the cache may not be the easiest thing to start off with. That doesn't mean that you should stop, but I just want to warn people that okay, this is not going to be a walk in the park. But regardless of all, what you decide to do, right? One of the things you realize is systems research, anything is not going to be trivial, right? The first thing you realize is systems don't do what you think they should do, right? That's the realization you come to the first time. I've seen that undergrad students say that over and over again. It's not doing what I think it should do, right? That's a perfectly valid sentence. It's a perfectly nonsensical sentence once you realize what I'm saying, right? It's not doing what you think it should do. It does what it's supposed to do. You just don't know what it's supposed to do, so you make assumption on what it should do, right? So don't wait till the last moment. It's already late. Make sense? And,
I guess I have a logistics question. How long are these presentations? I forgot.
So it depends on the class time divided by the number of groups.
Okay.
So you do the math, right? You won't have too much time. At the bottom line is you won't have too much time. So there's like 1, 2, 3, 4, 5 groups or 6 groups, 5 or 6 groups, right? So divide the time equally, right? So another thing, since we don't have too much time, I'm going to have to hold you to your time. So you will have to explain what you're trying to do quickly so we can kind of move on. So keep that in mind when you make the presentation, right? So if I tell you that you're going to have 5 minutes, don't talk about motivation for the first 5 minutes. Then I have nothing to base my evaluations of your project on, right? And it sounds trivial, but it's not. It's not easy to keep talking, as you may see from the lectures. overshoot, but it's a lot harder to be precise, right? Yeah.
Is there a way you could like talk about or post some past projects so that we can have some idea on what we work on?
I think I left some projects on the project website. It depends on where you're coming from. So my sense is the easiest projects are ones where you have some clue about what is happening, and that's one of the reasons why I think the things that bug you is the place where you want to go. For example, if you think that the machine startup time is very slow, if you want to see why it's slow and you want to monitor that, right? Then everything you have to do to answer that question comes naturally, right? But if I tell you, you will do a project to figure out the cache coherence failure in NFS, right? If you have no idea what I'm talking about, then you're not going to, it's not a project for you, because we don't have enough time for you to understand what the problem is, why it's a problem, how you may solve it, how you may find it, and all those things, right? So there's some guidelines, but I think the bottom line is go for something that makes sense for what you've done, right? So any project that you've done in the past, if you want to see how it performed, whether it can be improved and all those things, those are good projects too, right? So any substantial project, right? So don't take Hello World and see what you can do about it, but right. So have you written any kind of projects in the past? So what kind of a
like a file transfer in distributed system?
Yeah, try to see if there's something that you notice that you can worry about, right? Again, not the networking component, right? If you find out that the file transfer was slow because the network you're using was a dial-up, that's something we can do on the operating system level. But if it's something else, then those are good projects, right? So I'm there most of the. I mean, I can be there most of the time if you wanted me to. We have a deadline on tomorrow evening, so kind of busy on that one. But send me chat or email or whatever to kind of get an idea. But it's always good for you to have some idea before you come and talk to me, right? If you just say, I think I want to work on something on file systems, that's all we thought about, then the conversation is not going to go too far, because the possibilities are endless, right? So if you say this is what we're thinking of, does this make sense, then it's a more easier conversation, right? Yeah.
You mentioned this was a two-phase project. The first part was measurement, second part was analysis. Are you looking for both phases to be complete by next month, or is it just the phase?
Just the first phase.
Just phase. Okay. Yeah. When would phase 2 be done? Did you have a deadline for phase 2?
Last day of class.
Last day of class.
Yeah, or something thereabout, right? We had to find a time to do the presentation, but so you don't have to take the first project into the second project, but it's usually a good idea to do that, because then you have to come with a completely different project, right? So don't look at it as I'm not going to hold you to say, since you started this, you have to finish it kind of thing, but it's usually helpful, right? Does it make sense? And again, I'm not looking at how much code you've done or how much stuff you've done. I'm looking to see what's the analysis, what is your thinking, right? And again, it's okay if analysis is wrong in the absolute sense. Again, it's okay because we don't have the knowledge to come up with the best analysis, right? Because this is a course project, not a research paper or something. But it should sound right to the best of our knowledge, right? Does that make sense, right? And you'll know what it means when you get there, right? So to know exactly whether you're on the right track, you'll have to read all the prior paper on that area, and I don't think that's feasible for what you're trying to do. You have to know every piece of prior work, what they've done, how it relates to this, and all those things, which may or may not be possible, right? So the other option is to take one of the papers and see how things are right now, right? The threading performance or event performance or what have you, right? Okay, so that's logistics for the paper. And so was this paper easier to read? So did the email make sense? The one I sent you about the events, right? Did you understand what I was asking on the event stuff? Yeah.
Not quite. I understood, but what was the answer you were looking for, I guess, is what it amounts to in the email. You were talking about, was it going to be easy or not to implement the prints? You're talking about the print statement.
Yeah.
Was it going to be easy or not to implement the print command?
So there are two prints, right? One which says that I noticed an error in sending something, right? So the code basically was trying to do was algorithm, what it's trying to do is it gets a URL request from somebody, right? It gets a request from somebody. You read a file corresponding to it, and then you send it off, right? So you split it up, you rip it up to say the URL you get somebody, you parse it to figure out who the answer should go to. You split it into this request should be done by this particular file, right? You read the file, and now it becomes a bunch of bytes, and you give it to the next section, where the next section, all it has to do is send this bunch of bytes to the receiver, right? Now you get a problem when you're trying to send it to the receiver, right? So how would you print error message? We have seen error messages like this all our life, right? So it says, one error message says, I have a trouble sending something to yahoo.com, right? The other error message says, I have a trouble sending error message to yahoo.com while I'm trying to answer something, right? While I was trying to, not yahoo.com, I was trying to answer to this person. The second answer says, I was trying to answer to this person for this particular file, this particular URL, right? So I'm asking, are these two error messages, are they equally easy? One is harder, one is easier, and what would you do to give the error message, right? We've seen those error messages all the time. You know, sometimes it says error in printer or something, right? And you have no idea what it's talking about, you know, because you send like multiple print requests and you have no idea where it might happen, right? So if you ask multiple requests, all it says is, I have trouble supplying requests to that particular user, right? The second case, it says, I have trouble talking to them for this particular request they asked, right? Are they the same complexity? Or is one of them easier, one of them harder? Yeah.
I think if you want to, the sender doesn't know about the URL. It's only know about the receiver. So if you want to print out something like, I have trouble sending this user this URL, then you need to pass the URL to the sender when you specify it.
Yeah, so you would like the second case. So you would like the second case, but it's not, the way I wrote the code, it's not obvious that you would have done that, right? If you wanted to put a printf, you would have had to store the stack value for the URL to the magic function. If you didn't do that, you can't just put a printf, right? So if you wanted to add that into a program, just do a printf statement, you'll have to change your program, right? You have to basically change your program to now magically store the URL before retrieving it. That's one way it'll be different, right? The unripped program, I can just put a printf anywhere I want, and all the stack is there. Whereas the ripped program, a simple thing as I want to print the URL which is requesting it won't be available to you unless you remember to store the stack. And if you didn't store all the stack variables possible, and this one would have been in some variable somewhere, and if you didn't do that, if you forget that, then your printf will fail because it does not know what the URL is. So then you have to go and muck around the code. So that's one of the annoying part of the event-based system, right? When you have an event-based program, you have to understand what's going on, right? If you don't understand what's going on, if you didn't store some variable properly, then something which you think should be natural won't happen, right? And the reason why you don't store everything is if you do store everything, then your stack becomes bigger, then the amount of things you have to store becomes bigger, right? So that's the sense, right? So this paper is also in the similar vein. So you'll find that we're not going to talk about threads and processes and stuff because that was covered in undergrad class. But what we're trying to look at is a lot of things that we assumed or didn't realize the performance cost of those are what is being discussed here, right? And so the first paper is on continuations, which is considered a classical paper. So what is this paper talking about? What's the problem being solved here? And by the way, this precedes the papers we read yesterday, right? This was read in 91. The papers yesterday were way beyond. 95. The Austerholt paper was 95. The others were in 2001 and 2003. So those were newer, right? This was before all of those, right? So what is this paper trying to address? Yeah.
They're saying that the two main ways, there's two ways to implement thread management. That when threads block, you either save off the entire stack to be restored when the thread resumes, or manually save off only what you need. And so saving off the whole stack is very resource intensive, it takes time and space. but only saving off what you need can be difficult to maintain, especially if the code after you refers to something above you and you don't know whether you need to save it or something. And so they're trying to find a way to balance out those two issues to somewhere that will be efficient but also easier to maintain.
That's an excellent summarization of what they're trying to do, right? So what's the cost? Did they understand what you were saying, right? So what is the cost of it? They didn't like say too much about it, but what's the cost of doing this, right? What are the costs you can think of doing this all the time? Who wants to? Right. Yeah.
Well, they talked about the like 4 kilobytes or something for each thread, and if they could save that in the kernel, that would be incredibly useful to reduce the space.
Yeah, so the savings is in the amount of stack that the kernel has to reserve for you, right? And so what are the costs? Actually that's the savings, right? Not the cost. Right? Yeah.
Well, the programming, you're going to have to redo your kernel, I guess, to rip apart the processes.
So this is essentially what I was saying in the email and what the last papers are talking about, right? Now your program is no longer this simple stuff, right? I mean, whatever you assumed as a simple way of doing, now you're coming in and patching the stuff to keep these states around and all those things, right? Is that easy or hard? Yeah.
So, I mean, from the software development perspective, when you have to manage a large project, I mean, this thing would scale up. And you have to, I mean, the programmer has to decide when to use the one approach or the other. I mean, this would complex somehow the code. So
scale up meaning like scale linearly or scale non-linearly? What is the gut feeling? Scale linearly would mean that, so what I mean is if you wrote a program of 1,000 lines, it's 1 times harder. If you wrote it 10,000 lines, it's 10 times harder, right? That's roughly what you expect, right? Non-linearly expect, 1,000 times is 1 times harder. 10,000 lines is 100 times harder, right? So it's becoming more and more complex as the number of source code increases, right?
My feeling is it depends on the application because you cannot really foresee the number of levels of recursion or function calls. So if I paraphrase what you said, it doesn't depend on the number of source lines. It depends on how complex how much you have to use this stuff, right? So if you does that make sense, right? So if you have a program which uses only once this technique and something which uses 10 times this technique, right? You should only count that, not the number of lines, right? So let's talk about those. So if you have a program which takes 1 time and another one which takes 10 times, would the 10 times be 10 times faster, 10 times more harder, or much more harder than that?
Depends if the 10 times are regressions. In other words, is it one calling, another one calling, another one calling, another one, versus just 10 identical calls to what you had in the first time? The regression, I think, would be a lot harder to program.
Yeah, I was thinking of the regression. I mean, 10 different things, right? So,
don't they say in the paper that it was relatively easy once they had the first thing done to move it over to the exception handlers? So shouldn't it scale?
So why do you think? So I maintain that it's going to be harder, right? So let's say I'm taking the devil's advocate position, saying as you make it more, as you have to do it more in a fair sense, like not the repeating stuff, it becomes much more harder to deal with because now there's so much state which used to be in the logic in the program now has to be here because the state is spread all over the place, right? But they claimed that when they moved it from one to the other part of the system, it was not that hard, right? Do we contradict each other? Obviously we are, looks like, but is that a contradiction? So they do address this. I mean, it's not that they don't address it, and they even have section on software engineering aspects, and they make a claim that it was not that hard, right? What is the basis for the argument that it was not that hard?
I think the basis is the 99% of the threshold is only results from the 6 points there. So that's the core of their theory. So
right? So which goes back to this stuff, right? Like the one you mentioned, it's not the number of lines of source code, it's the how many times you have to do it. And in this case, you'd only have to do it for 6 times, so it's kind of okay, right? So would you do this on a kernel where you write from scratch? So suppose you were tasked to write this kernel from scratch. Would you use it with continuations, or is it easier if you had to retrofit a kernel which is already not using continuations? In their case, it was retrofitted into a kernel, right? Mark III did not support continuations. They analyzed it and they said only 6 of the 60 was a problem, and let's fix that, right? What if you were to do this from scratch? Would it be easier or harder? Yeah.
I think it's significantly harder because you might end up trying to do everything in continuations and maybe unnecessary performance and debugging extremely.
Is that's my gut feeling too. I mean, is that how it sounds like? Right. So one bit of history of how Mark came about, right? I'm not sure how many of you understand the history of how Mark came about. It's there in the paper, but you have to, I guess, know how to read it, right? Because they're not trying to make it sound worse than it was, right? So Mark, like any academic project, in fact, any operating system out there, right, was not written from scratch, right? And we all realize, I mean, we were just talking to you about Windows and stuff. No. Operating systems are a sufficiently complex piece of code that people rarely say, okay, now we're going to come up with Windows Vista. Let's throw everything we know out the door, right? So now we're going to start from scratch. You write the file system, you write the process thing, you write the stuff. I'm going to write the main, we're going to start the project. We don't do that, right? Because it's just so complex. You take existing piece of code and you start to modify it, right? And sometimes it's linear modification. You just add more features, you make something more optimized. Sometimes it's completely non-linear, right? You kind of you completely change the way things are done, and then you kind of move on, right? So in terms of Mark started off as an operating system for a specific piece of hardware, which was good at doing certain things. It was good at like doing I forget what they were saying. There's hardware support for, I believe context switches, right? Which made this problem did not happen for the original Mark kernel, right? So they built that kernel and then they ported Mark to different platforms and stuff. So they had Mark. So and then they found that Mark was not exactly BSD, because BSD was what everybody was using, at least in academia. So you couldn't use this machine because there was no application, there's no software on top of it. So you had to build a BSD thing on top of it. So this is Mark 2.5 before what the more recent Mark. So it's still a monolithic kernel. So he still had one kernel underneath. He had to glue this BSD stuff on top of it. So now it talks BSD. So it translates whatever you're asking in the BSD system down to whatever it has to do underneath, right? So that was then. And then they decided that this is not a good way to go because they wanted to research on microkernel, right? So they sat down and put them on a big piece of paper, printed the whole code, put it up there. Then they decided and said, okay, we draw a line here. This should go in the microkernel. This should stay on the user level, right? So there was not a complete rethinking. Not, you don't go into a room and sit down and think about what should go on a microkernel, what should be an application level, and go from there. Rather, it was you take this 2.5 and then you kind of split it, and then you did this. So they inherited a lot of the stuff because it has roots from the original Mark, which was ported over to 2.5 and then came to 3.0, right? And one of the examples was the notion of the event-based handlers or thread handlers, right? The thread handlers come to them from a monolithic kernel perspective, which is where they get all the stuff. So had they not treated it as a thread-based system, but event-based system, which is what other operating systems that they refer to like system B and everything. If you had followed their model, then you may not run into this problem, right? So one of the two things they mentioned is you can have a process mode operation or an event-based system, right? In process mode system, every time you have a thread, you have to have a stack for it. So if you have a thread inside the kernel, you have to have a per thread stack, right? Because you need to keep track of where things are. And it's especially true because if you inside the kernel, if you have multiple threads, and if one of the threads has to block, right? If you don't save the thread state, then things will fail. So you have to either, when you go into the thread kernel, you have to either let it finish all the way through. But if you want the kernel threads to block, then you have to store the state, right? That's the process model, that's the price you pay, right? The other model is if they had done an event-based system, then you only need one stack, right? So per processor. So each processor, like we talked about in the previous class, will only do one thing, one system call or whatever. So it'll have to do the system call, finish everything, and give it back. So you could have, life could have been easier, right? But they couldn't do that because they decided that this will all go through on the single kernel, right? Before you think this, like the kernel level threads are easier stuff, if you look at the commercial operating systems, right? So I'm not sure of the state of Windows Vista or the Mac OS X 10.5.4 or something, right? The kernels were typically not very multi-threaded, right? Because it's a lot harder to deal with kernel level threading. So when we first came to multiprocessor machines, most of the kernels tended to be to use only one thread inside the kernel, right? So you may have realized it or not realized it. So from mid-90s and stuff, when you started to get multiprocessors for your desktop, you can have multiprocessor applications on the top. You can run multiple threads and what have you. But when you get into the kernel, they were only using one thread, right? So it may show up as they may use only one processor to run the kernel. So if you have multiple processors, if you have 4 processors, they can say all system calls will have to go to processor 0, right? So everything has to go to processor 0. And that's the easy way to solve this problem, right? Easy way to solve consistency problem is to not even have a possibility of inconsistency, right? So if you remove a notion of threads, right, then life was easy, right? But this is talking about what if you wanted to make the kernel multi-threaded? I mean, if you have multiple processors, why should the kernel be only running at all the kernel processors should run only at one thing, right? So that's when it comes, right? So why would you want to run the kernel on all the kernel processors and not just on one? What would prompt you to do that? You have, let's say, 4 processor machine, right? I have one kernel where all the system calls will be handled by one processor. I have another kernel where it can be on any of the processors. Why would I choose one or the other? Why would I choose the kernel on only one processor architecture?
Because then you can theoretically handle 4 system calls simultaneously.
Mm-hmm. Yeah, you can do 4, right? But why do I care? Why would I care?
Wouldn't that make things more efficient? I mean, everything would run faster if you could spread everything out. Even if you could spread the single-threaded applications out across 4.
So what has to happen for that statement to be true, that you will get better performance? Yeah.
If you have the application and the kernel that it's trying to use on the same processor, and there's some reason that you need the processor like I/O that kernel can handle.
That's one reason. Yeah.
I think the major problem is when we make a system call, suppose if there's multiple kernels on multiple processors, the problem is which kernel will handle this call.
Let's not get the technical aspects of it, right? I'm saying somehow we solved it. I'm saying one aspect is, I mean, how to do that is very hard. That's some of the things that they're dealing with, right? But I'm saying, let's forget how to do this. All I'm saying is, your one kernel says all the system calls go to one processor, right? The other one says it was very hard, but we eventually solved it. Now we run it on all the 4, right? But I'm saying you as an application developer, let's say, why would you care for one or the other? What would make you go like, that's what I was looking for? And what would you make it go say, no, this is fine, good enough, right?
Well, if you go back to, for example, I think Windows NT running on a 4-processor system, or even I think this is true of Windows 2000, if you would expect a 4-processor system, your applications would run 4 times faster, but they weren't getting that. They were getting only about 2.5 times because they had the problem of having to have your kernel run on a single processor. So all the calls had to go to that processor, and that was literally keeping you from taking advantage of all the processors.
Yeah, I think all of you are coming you're saying the answer, but not quite the way I was expecting it, right? I think that they have it in the paper at some point. I think what happens is, if you don't want any kernel resources, it does not matter, right? I mean, clearly in this case, so if you had 4 times the processor, right? 1.5 time of the application was being used by the kernel. That's the assumption, right? So does that make sense? So let's say you have 4 processors, right? The application was getting 2.5 times performance, right? You're getting this one, right? And he implied that this is not good, right? He implied that he would like to get 4x, right? You may be right. I'm just using the word implied to make it sound like there's a conspiracy, right? So what is his basis to assume that this is good and this is not good? It seems self-evident that you would want 4 times performance, right?
You're paying for 4 processors.
Yeah.
It costs some overhead between the processors to synchronize. They share something. Yeah.
So there's an application level sync overhead, right? So you're saying, if you consider application level sync overhead, you may not get 4, right? What other reasons could it be why you get this much?
I/O overhead.
Okay.
For I/O the whole time.
Okay, this is a good answer, right? I/O overhead. What does it mean? What does the I/O overhead mean?
Data can only come so fast.
So that argument says that this system can only run at 2.5, right? So if you go to 16 processor, right, this particular program cannot go faster than 2.5 because of I/O overhead, right?
Like the memory problem?
Yeah, the memory problem. So the bottom line is, there may be some reason why this application can only wants 2.5, right? I mean, it does not want more than 2.5. So you can't make a system go faster than it has to go. I mean, there's a basis of how fast it can go, right? So there's some reasons why it can't go, right? So we have to ignore those cases, right? So there are cases where it does not happen. So if that happens, it's not a thing, right? So let's assume we go into a case where you can clearly show that this particular application could benefit to 4x, right? And so in that sense, the overhead might be the application level overhead. The other overhead is the kernel overhead, right? How do you see a kernel overhead in your application? How would you see how much kernel overhead you have in your application? How would you measure it?
Time spent in the kernel.
Yeah, time spent in a system call, right? When you make a system call, when you call the kernel, time spent, right? So unless you have reason to believe that 1.5 times of your program running time was being spent in the kernel, right? We don't know no basis to go with that argument, right? That you have to have the stuff, right? So it all boils down to how much of the kernel do you really use, right? If a system only uses 0.01x of kernel time, right? Then the approach of putting everything into the processor 0 sounds fine, right? I mean, yeah, you can spread it, but why bother, right? I mean, the ratio of kernel to application level code is in the favor of applications. So worry about the applications, don't worry about the kernel. It's so small, don't worry about it, right? If the kernel is using lots of resources, if your significant portion of your program is running in the kernel, then you need to worry about the stuff, right? And actually, they do say something about this stuff. Do you remember what they were saying about the kernel? How much you need the kernel? I think on page right before 1.4, they mentioned that multiprocessor applications tended to shy away from kernels. but multi-threaded applications tend to love calling kernels, right? So what does that mean? Like, so what? And they don't actually go too much detail into that. They just mention it, right? So what is the intuition behind it? Why do you think multi-threaded applications call the kernel a lot? Can you think of a multi-threaded application that you could? So what is the benefit of doing multiple threads rather than multiple processes, right? This is from your OS undergrad class, right? The standard exam answer, right?
Shared data structure.
Mm-hmm. Shared data structure. The other one?
Well, less overhead in terms of.
Less overhead.
If you thread blocks, you can switch to a different thread of execution.
Yeah, so if you thread blocks, you can switch to another thread of execution, right? That's one of the things which are touted, right? I mean, when you write a threaded program, don't worry about anything. You can make a blocking call because then you can fork another thread and keep going, right?
Yeah, just mimically parallelism. Mm-hmm. We call one. You can imagine that 2 or 4, more one.
Mm-hmm. So yeah, so basically, so in the undergrad class, we encourage that, right? If you want to do blocking call, just go ahead because fork another thread and that'll do something else, right? And that's coming back to bite you here, right? So people apparently listen to that stuff. So now they create more threads because creating a thread is easy. And if a thread has to block, fork another thread, right? So even though they don't like harp on it, I think that's coming back to bite you here. I mean, when you write your programs in undergrad, I don't think you were taught to be careful on how many threads you create. I mean, you're probably taught don't create like 1 billion threads because, I mean, any good thing would suffer when you go to that number. But you create threads. So when you create lots of threads, how does this problem come about, right? So suppose in your application, so now we have this is the kernel, and this is the user, right? And you have multiple threads coming in, right? Because you're just calling thread every time you wanted something because it's easy to create. Where is that problem? Would that be a problem if you map all this into one kernel level thread? Remember, this is one of the things that we do, right? We don't have to map application level thread to user level thread, right? You kind of do a mapping, right? Would this be a problem if you were to do something like this? You said yes.
Protection.
Huh?
Protection.
No, I'm saying like this library maintains all those stuff, right? Like if you use a pthread library or something, assume that the semantics are the same. I mean, you use a pthread library, all the protection, all this is the same, right? If you use a single thread and map all the user level threads to the single thread, I mean, this is one topic you read about, right? It's a user level thread package. It's done correctly. So let's assume it's done correctly. So, right, all the semantics are the same. Would it solve the problem we run into here?
You're going to have an awfully large kernel thread, though, aren't you? Isn't your kernel thread going to be fairly large if you've got a lot of user programs coming in there?
What do you mean by large?
In terms of the amount of memory that's required.
No, because the memory stuff would happen here, right? So each one will have to have a stack, right?
Yeah. I see what you're saying.
But there's only one stack inside the kernel, right? So at the application level, yeah, you'll have multiple stacks, and you have to deal with that at the application level, right? At the kernel level, you see only one thread, right?
If everything is a syscall at once, then you're going to be stuck on your single core, assuming you have multiple cores.
Yeah. So in other words, you lose parallelism up here, right? So this is a good solution for this problem, and I can solve this problem by doing this, and that's one of the things that they mention in terms of using C-threads library, right? They call it C-threads. C-threads kind of died out. C-threads was a much higher performance package than P-threads. P-threads is for portable threads. C-thread is for, it works very fast on the particular machine, but at the end, portability won over C-threads. But essentially use a C-thread, you could solve this like this, right? you can map it into one, but then you cannot get all the processes. So you want to have multiple threads. You also want to be able to use all the processes. So this works in some cases, but at the end of the day, you have to be able to solve all these threads. So the problem that you're running into is you have all these threads with all the state, and every thread makes a system call, means that there has to be a kernel level thread if you do a one-to-one mapping, right? Every user level thread will map into a system call. So every system call thread, as long as it's doing something inside the kernel, it has to maintain its state, right? So it maintains a state here, application level stack. When you call into the kernel, it has to have a new stack. It performs whatever it has to do. If it has to block for whatever reason, when it comes back, it has to restore its own stack. And when it's finished, it has to purge its stack and then give the control back to the application, right? Why do you need a stack for kernel and the user? Can you reuse the stack from the user level into the kernel?
I think you could. Isn't that what continuations is trying to do?
No. Forget this paper, but I'm saying in general. Yeah, continuation, they don't use it blindly. I mean, they're there to use the contortions, right? So, but can you do that? Can you use a single stack for? I haven't heard much from you. So, can you use the same stack, both at the user level and the kernel level?
I don't think so.
Behind it. You want to guess why? I'll give you the answer. You can't, because I have two different stuff, right? Why can't you? You don't want to address it? Yeah.
You wouldn't want the kernel to because when a user program makes a system call, at least as a programmer, I would hope that when I get control back from the kernel, that the stack would be in the same state that I left it in.
Mm-hmm.
And you probably can't. I mean, if the kernel has access to my user level stack, then they could potentially change it, corrupt it, and then I'd be in trouble when I got it back.
Mm-hmm. Yeah, there are multiple issues, right? One is if the kernel corrupts your stack, when you get it back, then you're in trouble, right? There may be protection issues, right? In terms of doing this stuff. The kernel can always look into whatever you're trying to do, but the kernel does not want to use your stack because it can do whatever it wants, right? It's not bound by the user level stuff. So you don't want to share the same stack with the kernel. You need to create another kernel thread, right? Yeah.
Because you just modify the kernel stack as it's running, or you do something so that the kernel will have to block, and then you just go and you smash its stack up a little bit, and then you gain control.
Yeah, I mean, this is the one way to control what's going on inside the kernel, right? So kernel tries to be safe first and foremost, so it does not let the application. So if it was an application space, this thread can modify something into the stack, right? And if the kernel was using it directly, then the kernel is now, I'm manipulating what the kernel is doing through the stack, right? So in general, when you go into the kernel, you start everything fresh. So you have to have an own thread. So essentially what's happening is you have this stack, and when you're blocking, you have to save the stack elsewhere. So you have all this stack, which is another term for all the state that this one has and this one has. And that's bothersome. That's why they're trying to address, right? So why is it bothersome? And they answered that in the paper, the first few lines. So why is it not a good thing to have all kind of stacks?
Because they only had 8 megs of memory.
Yeah, so their laptops have 8 megs of memory, and then their servers have 32 megs of memory, right? But the kernel stacks were 4K, right? And if you look at any modern machines, no one uses a 4K stack for anything. Right? You can't go too far, right? So that's one problem. But did it scale, right? Is it a problem right now? I'll put it the other way. Is it a problem right now? In a modern machine, do you care if the stack is only 4K? I mean, obviously, right? I mean, most machines come with a couple of gigabytes of memory. A kilobyte here, kilobyte there doesn't seem like a big deal, right? Why do we still care about this stuff? or should we care? Is it an obsolete paper that should have been tossed out? So do you believe that the numbers scaled up? Meaning back then they had 8 megs of memory and 4K, right? So in the modern machine, let's assume we have 8 gigs, right? Did the stack go from 4K to 4 meg? Right? So if we had 4KB and 8 meg, now I'm saying today's 8 gig, do you think that you would have gone to 4 megabytes? Do you think this would have happened? The answer is not in the book. I'm just.
I'm not sure it does scale linearly though, does it? I mean, I don't know if you need a 4 megabyte stack just because you went to 8 gigabytes of RAM.
It's bigger, but I think it's static. Eventually, you have like more register, or more state to set, but it's not 4 megabyte. I think the problem is the processors, gets faster and faster. So your system is run as fast as the slowest part of your computer, assuming the memory. So first with this, I think you're an excellent point, but let's stick with this one, right? So so you don't think it's going to go to 4 meg, right? So what is this made up of? What is the stack? We've been talking about this for a couple of classes, right? So what is a stack from your perspective? What do you store in there, right? Your local variables and state program variables and stuff like that, right? So, right? And then you store your return addresses and stuff like that, right? Is this number related to anything that your program does, or is it related to how many, like let's say recursion, right? So if you do recursion, all your return addresses are stored, right? So is this number purely to address for recursion kind of state, or is it related to something with data, right? I don't know the exact answer to this one, so I'm trying to find out what the answer might look like, right? So is this, how much of it is made for program status, I mean the register values and stuff like that, and how much of it is for data, user level data, right? There is something which is done for program level, which would be the same whether you ran the program back then or right now, right? So that we don't have control over. And there's something which is used for data, right? Then the question would be, in the modern system, the program stat and then the data, right? We're trying to understand if there is a difference, how would this sort of translate it, right?
Most of the time when you allocate any big objects, you're going to allocate it on a heap, and you're only going to keep a pointer to it in the stack. So
how do you allocate stuff on the stack?
Well, it's a local variable.
It's a local variable, right? So local variables you allocate on the stack, right? So the argument is, from this time to this time, do you think the local variables would have gotten correspondingly bigger? Right? The answer may or may not be no. I mean, I think sometimes I feel like it's not true, but sometimes I don't think it's true, right? If back then they used a byte for integers, and now we use a 64-bit integer, if you use the same data structure, now you kind of made those things bigger, right? This is one of the costs of 64-bit machines, right? I mean, many of you have followed the 64-bit architecture. Everybody's happy about 64-bit architecture, right? Because 64-bit means you can store larger number, right? You followed that argument, right? Most machines you buy these days are pseudo 64 at the least, right? The cost of 64-bit is your integer now is 64-bit, right? Which means that it takes 8 bytes, right? So if back then they wrote a program which did integers which used to be, I don't know what they did. So when they do this, so it may not be obvious to you, but if you had an integer array of 100 and you use an integer array of 100 now, things would increase, right? So even though...
Would you really store 100 array integer or 100 index array on a stack?
So how many of you would have stored 100 integer? So how many of you would have done int I of 100 in a stack? None of you ever done this? He's saying no.
Well, I did it when I was
if that's a local variable, oh, I don't know what the compiler will do.
Oh,
Is that for
integer of 100 is not
Yeah.
that big, right?
It's, yeah, it's
How many of you done something like this, integer of 100 in a local variable?
Talking about homework in intro CS class.
Anywhere, any place. So, how many of you have done this in intro CS class? How many of you do it now? I would do it now. So you're saying that you guys don't do it because you're aware that there's a stack.
It all depends on what you're doing. If you're going to do massive recursion, then you're going to have the stack with 100, or I mean, it just doesn't make sense, right? So it all depends on your application.
Yes.
I'm still doing it.
So if you guys, okay.
Yeah, that's the problem about the compiler for the optimization. For the big read, probably I could allocate the storage on the heap, you know.
No, it has to allocate it on a stack. Because the semantics of, you can't do that in stack, right? So except I do this, right? I do this all the time, right? Because I do it till if I recurse by accident and then it code I'm saying stack overflow, or I get something, then I know what happened and I move it out, right? But so I only do it after I notice a problem, right? So if I'm the only one and you're the only one who does this stuff, and the rest of you are aware that you're using something on the stack and you want to avoid the overhead that you're going to face in the kernel in terms of all this stuff, then my job is done, or more power to you, right? But normal programmers don't think that hard, right? Because 100 sounds like a small number, right? I would never probably do 1,000,000 here because that sounds like a big number. And I think 1,000,000 is the largest that the C compiler would do. I think if you go over 1,000,000, it tells you there's a large array in stack. How many of you have seen that error? I think 1,000,000 is what I've seen in the GCC, right? So some of you have seen the error, right? So you go to 1,000,000, you get some error, and you kind of think about it. You're like, oh yeah, 1,000,000 would be really 8,000,000 bytes on the stack, and you get a stack overflow and all those things, right? But most people, as far as I used to think that most people don't think about that, but many of you seem to worry about those stuff, right? So that's one of the cases where you get the so I'm saying back then I wouldn't have talked about 1,000,000. I would have looked at 100 and I would have said, okay, I know that my systems had so little. I mean, I wouldn't have said compared to 2008 I had so little memory, but it was painfully obvious to me that there's not much memory and we have to do all kind of stuff, right? This is the time when DOS was not even, I don't know if it was probably there, but life was a lot different. So you were counting bytes and stuff, so you probably wouldn't have done 1,000,000. But now it seems like careless, right? So I'm not really convinced that this didn't happen linearly, right? I think it's more realistic. So actually it's not 4 gig, right? It's mostly like 2 gig. So this should have been 1 megabyte. And I think it's actually more than 1 megabyte, right? Typical machines are not 8 gig, right? It's more than 2 gig. So this should be like 1 meg, right? 1 megabyte is not a big number, right? Because for example, GCC lets you do 1 mega integers on the thing, which is 8 megabyte, right? So stacks are bigger, right? So at least some proof that this problem is not the thing, right? Is there another reason why you would worry about this stuff? Is that the only concern? If you could make this stacks bigger, would it go away? They do touch upon this, but they don't stress it, and I think that's one of the reasons why this is still very important. I think they mentioned this 3 times in the paper. They say, yes, the stack is smaller, 4K and all those things, but there's also another potential use which they couldn't possibly stress back then because their machines seemed so pathetic, right? 8 megs, you're like, how did they ever, why don't they get a faster machine, right? What's the other reason why you would care about continuations at all in a modern machine where memory seems to be plentiful, right?
Yeah, in one sense, when the things get bigger, that does not mean it's getting faster.
That's what?
It's getting faster. The speed and the capacity is not linear. Yeah, you get bigger things, you probably slower. So if you get a stack big, it probably cannot fit in the cache. So
Okay.
it's slow.
That's the key, right? You get slower, not because it gets slower because there's more data, right? It goes slower because of caching effects. Your TLB gets messed up, right? So when you go from here to, if you go, the more you create this stuff, right? The more stack you create. Now you're going from one working set to another working set, right? You had one set of addresses in your instruction cache. You had one set of stacks, and you're doing something. When you do this context switch, even if you had enough memory to deal with this size, right? Now this one is in a completely different address, right? By definition, it has to be a completely different address because it's a different thing. That means you're going to pollute your TLB every time you do this, right? Of course, you'll pollute it because you're going from kernel user to kernel. But within the kernel, if you create new threads, forget about the protection issues. If you create multiple threads within the user space, if you create multiple threads within the kernel space, even when there's no protection issues, even when you can reuse the TLB, the more you create these new stacks, even if you have enough memory for it, you are polluting the stacks, right? The TLB, sorry, the TLB cache entry, right? That'll probably hit you a lot more. They mention it. They mention that there are TLB issues and all those things, but they had no basis to worry about it. And honestly, I have no idea how bad this is for modern TLBs, because I haven't seen a paper addressing those issues of how bad having these things are for TLB hit. And I suspect it's quite bad, right? Because TLB size hasn't scaled. I mean, TLB, if you take a hardware course, right? Building a TLB cache is very complex, right? So it hasn't grown from back then to whatever it is. The TLB size is like, few hundred entries at most you can hold. You're not going to be holding million entry TLBs anytime soon, because it's just the amount of hardware you need is pretty complex, right? So I think this is a lot more a problem now because of TLB issues, not so much as the memory issues. But it's still the same. I mean, you can, regardless of what maybe, the reason why you run into problem may be different. Maybe it's because of TLB, maybe because of the amount of memory. But the net effect is the same, right? If you have this kind of multiple threads, it's not feasible to solve it. So that's the thing. So that's one of the reasons why we should worry about this stuff, right? So can this be solved by using a I gave a big spiel about the history, right? I mean, they did this to come up with a Mark 3.0, right? So if they had started from scratch, would they still have run into this problem? I'm going to say probably not, right? Because if they start from scratch, let's assume that they would have realized this is what is happening. They would have, let's say, they designed it with the event-based model, where naturally it will be one stack per processor, right? So let's assume that's the answer, right? So can we say the real problem here is the Mark people got lazy rather than rebuilding the kernel from scratch? They just tried to retrofit. They tried to hack the existing Mark kernel, which used a process-based system for historical reasons from Mark 2.5 and 2. From whatever. The best solution is to kind of dump the whole Mark 2.5, start from scratch, and do it. That's a valid argument, right? Can I make that argument? No, of course I can make the argument, but is that a good argument?
Can you say something about that?
Right.
In the paper about how they thought about switching, but they decided against it for some reason, which I can't remember off the top of my head.
I think it's very hard. I mean, I think changing one of the reasons, I think somebody mentioned it at some point, that Mark is not used that much in stuff, right? I was involved with Mark project in '93 and something like that. It's the worst piece of code human beings ever wrote, right? Because it went through so much stuff, right? Take your best course project and give it to like 10. So if you go to the Mark publications project, right, there's like 10 or 15 PhD students who got their PhD out of it, right? So one of the things that you do as a PhD student is you can either write beautiful code or you can graduate and get out, right? How many of you choose to write beautiful code? don't say you are, because then I have to talk to your advisor and say, beat him up, because at the end of the day, your goal is to graduate, right? So you kind of change something and all those things, and then you kind of move on. So the code becomes mutated, and now it's like a big mess, right? And to fix that would mean that you have to go through and redo it from scratch and all those things, right? So there's tremendous amount of money put in. I think DARPA threw